All right, hi everyone. Today we're going to look at doing some heap exploits, and we're going to look at how a security library called Hardened Malloc can help mitigate some of these problems. So the C program that we're going to be attacking is from Exploit Education's website, and it's their exercise heap 0. So the idea of heap 0, the idea of this exercise is, instead of having this function pointer point to the no winner function, we want to make it point to the winner function. So the first thing that we got to do is learn where this winner function is. And after doing an object dump and dumping out all the functions, we see that winner is at this 401176. So the idea is to make FP change from 401187 to 401176. And we can do that because there is a string copy call, a direct string copy call without the string end copy. And it's taking in arbitrary input from the command line to do it. So the program, I'm running this on my machine here, and I compiled it with these C flags. So there's nothing special going on here. We'll get into these later, but right now I want to just show the exploit itself. So let's take a look inside of H0, and we're going to do set disassembly flavor tell, and let's disassemble main. And here's the program, and we're looking for that string copy, and here it is. So let's set a breakpoint there. And let's just run the program with 4 A's as our input. And take a look at the registers, and we can see register 0 here. Or register RAX. So let's print out what's in RAX at the moment. And where are we? So we're right before the call, and we saw that our memory region is all empty, and we can see this pointer to the FP. This pointer to no winner here. So right now in the code, we are at, I'm going to need to redo this because I've done some hacking on this level 1. So let me clear this off first, because we want to use what we've got from the website first. So let me move this heap 0 to heap 0 mic. And we want to copy in this code. All right, let's take a look again at the heap 0 program to see where the functions are. And they've got similar, exact same locations as my little hacked up one that I was using to just kind of learn a little bit more about what was going on here. So let's jump into GDB again, and let's disassemble main. And we want to go after that string copy. So, and just for this time, we'll go at the same word too. So let's run with AAAA. And let's dump out the RAX register. And as seen before, a bunch of zeros, and then we get that no winner program. And that's because we are right before we execute the string copy. So we've done 2 mallocs, and we've set this FP to no winner. So if we continue on and go to right after the string copy's done, and take a look at RIX again, there's our A's. So what we can do here is we can overwrite all of this stuff. One important thing to notice is that this 51 is there, and that's the metadata for the F pointer. So the 51 in hexadecimal is equal to 81. And we can see that the size of FP, size of the pointer to F, should be the size of a function pointer. So that's 64 bits plus, so should be 8 bytes long, plus 64 bytes minus another 8 bytes long. So it should be 64 bytes. However, the size given to it has been 81 bytes long. But we don't really need to worry about that right now. All we need to worry about is that we want to overwrite all of this stuff up to and including this area here. So let's do that with Python. So let's make ourselves a little Python command line script. And we're going to do that by python-c, and we're going to print out. So we've got 1, 2, 3, 4, 5. 5 times 4 times 8. Times 4 times 8. 160 bytes that we need to overwrite before we put in our the winner function pointer. So let's just do a write of let's print out 160 A's and see what that gets us. So we want to run with backtick python-c print a 160 and end the backtick, and we'll run again. Yes. So we are at the string copy right now. So take a look at RAX, and it's empty. And let's continue to after the string copy and take a look at RAX. Oh, we've gone far too far. So my calculation was incorrect in that it's not 5 times 4 times 8, it's 5 times 4 times 4, because each one of these is 4 bytes long, not 8 bytes long. So 80, let's try 80 this time. Okay, and RAX is what we expected. Continue on, take a look at RAX again. And what's interesting here is that this is no longer 1187. However, we have not overwritten it, so I'm not quite sure what happened there, but it is unimportant because our exploit should still work. So what we're going to do here is now add in some hexadecimal code to say go to that 40, 11, and where was it again? It was 401176. And we need to reverse it because of endianness. And let's just make this easy to copy and paste. Alright, so right before, take a look at RIX. Nothing there, continue. Take a look at RIX. So now we've changed that value to the value of the winner function. So if we continue on, we should see, congratulations, you have passed this level, which is the printout from the winner function. So that's a problem. How do we fix it? I'm going to get rid of the Hardened Malloc that I have on my computer so that we start from fresh from the GitHub source. Now, Hardened Malloc comes out of the Graphene OS project. It's made by a fellow named Daniel McKay. He's the maintainer of the Graphite OS Android replacement operating system. And I hope I've pronounced his name correctly. And we're going to clone the repository. Let's go into the Hardened Malloc area and let's just dual make, see if everything works. Few warnings, but let's not worry about that right now. We've got the Hardened Malloc SO there. Okay, so let's get back into running that exploit again. Actually, let's run the exploit directly from the command line. So just that you can see that it's not any GDB trickery that's going on here. So take that, and it is input into the H0 program. So argument one copy. What's going on here? Why didn't that work? Oh, we did it wrong. It's not standard in that we're putting in. It is a command line argument. So paste it in. Ta-da! We've passed the level. Okay, now this time, let's add this Hardened Malloc as a preload. Let's run H0 with the same command line argument and see what happens. Level has not been passed. Okay, well, why is that? And in this case, let's jump back into GDB. Take a look at H0. And here we're going to set the environment variable preload equals code hardened malloc lib hardened malloc.so, and let's run with that script. Actually, let's set our breakpoints first. And now we will run with that script. All right, so info reg. Oh, this is a much different area than previously. Can we still take a look at that memory? right, it's somewhat the same. It's all empty at the moment, but you'll notice that this doesn't look like that winner program, that the no winner function. So what are we going to overwrite? Well, I'm not sure. Can we print out more? Let's print out, say, 1,000. And we're looking for that 401180, I believe the name is. I'm just seeing a whole bunch of zeros here. I don't see 401180. 401187. It's way down here. So there's all of this space between here, which will be the D name area, and way down here is our no winner function. So that's why, if we continue here and take a look at the memory again, here's all our A's, here is our overwriting. Well, what we previously overwrought, but it's obviously not the same as up here. So this is at that spot. Let's throw this into the text editor so that we know where we're dealing with here. So this was D name, and this was F. Was it P? The name of the F to FP. So if we continue on here, we fail. Okay, well, let's run again. All right, so let's take a look at RAX again. So again, we've got zeros. We've got something here. I don't know what that is. Not important for the discussion right now. And here is that no winner function, and it's at let's continue on and take a look at RAX again. So it looks like in this case, D name stayed the same, but the FP is different. Oh, actually, D name got what was. Well, they're just different. So let's see how different they are. So they're both values have the same starting set of bits, and only the last three digits here, the last three hexadecimal digits are different. So let's do a little bit of math on the calculator here, and we can see what's going on. So in the first run, we had a difference between the two values. The location difference between the two values was 550 bytes. But in this case, the difference between the two values is, it's not 550. Oh, no, it's 4B0. So there's different spots. So let's run one more time. Level's not been passed. And we'll run one more time just to see what happens again. And take a look at RAX. So a bunch of zeros. And Where's that? Oh, it's way down here. Okay. And continue and take a look again. This time. So as you can see, again, it's at different spots. And it looks like it's just like the last three digits are different. So let's take a look one more time. And F. So F50 minus 3C0, B90. So what's happening here is that there's randomization upon so because these two values are relatively similar size, they are being kept in a single M map. So let's take a look at the info proc mappings, and we can see that what we're looking at this time, F0, 4F79. So can we find a 4F79? We've got two 4F79s here. 7122. 7122. Oh, okay. And we're in the sixes. So this is the memory area. This is the memory mapping, in fact, upon where both of these values have been malloced into. So the malloc is allocating room inside of this memory mapping. Mallocs of different sizes. The way that that lib hardened malloc works is that there's various different size classes, and take a look at the documentation. It might be a little bit more helpful. So these different size classes mean that different memory map system calls and memory map allocations are done for those different memory classes. So because these are both, they're both bigger than 80 but less than 96, they're going to be in the 96 class. Now this slab is 4 kilobytes large. But they're inside of this memory mapping, the malloc is doing some randomization so that each malloc in this slab is going to be at a random spot, and that's why we're jumping around at different spots every time we run the program again. And that's one way of making sure that an attacker can't craft some exploit code to overwrite the known area of where this function pointer is going to be. Now, just to show you, just to run this function a few times with without lib hardened malloc again. First, let's set some breakpointers. And we're just going to go for the one afterwards because that's all we need at the moment. So set our break and we will run our code. And let's show off the RIX. So x64wx. So we're at 405670. And I'm just going to run it one more time. We already know that this will exploit it. Let's try it again. Take a look at RIX. The same spot, and this one's at the same spot, and just third time for fun. So every time without this lib hardened malloc, the mallocs appear to be going to exactly the same place every time. So that means an attacker can craft an exploit to make sure that he or she can overwrite that function pointer with regularity. With hardened malloc, with Hardened Malloc, we can see that things are in different spots. Now it's interesting. This is me. That's my exploit code. So as you can see, there's randomization inside of these slabs. So that's I think proof enough that lib hardened malloc is a useful security tool in our tool chest, and I think that we should use it. However, there are other ways in which we can stop this exploitation. And I want to show some of those off as well. So there are other ways in which we can stop this heap overflow exploitation. And one of those ways is to use Clang and to use the sanitizer CFI, which is code flow integrity. So what I'm going to do here is I'm going to recompile that heap 0, but I'm going to add these flags for control flow integrity. All right. So we've compiled it for control flow integrity. So let's just take a look inside of GDB of H0. After we input our assembly code. After we input our exploitation code. So, and we are after that string copy, so RAX should include the A's and the exploit. So let's take a look. And it does include the A's and the exploit. Actually, let's take a look at. Well, let's just continue on, and you'll see what happens here. We got a sig-ill illegal instruction, and that's even though that's. I'll break it down a little bit more. So we will run one more time, and we've copied the stuff in. So let's step over. Step over, step over. Where are we? Step over, step over, step over. And step over again. Step through. Step over. Oh, right here. So for some reason, it doesn't like that we've changed that pointer. And I'm not an expert or anything on this CFI. Not that I'm an expert on lib hardened malloc either. I just thought it was interesting. But for some reason, CFI makes sure that the code that is expected within main is the code that's going to be executed. And because winner is not in main, it is not allowed to be executed. So let's do a little bit of a change here. Let's call winner so that it's still in. It's now in the control path of this main function. And let's try it again. Continue on. We need to run with our exploit. And so the memory looks the same. And when we continue, we still get this sig-ill, even though we've added winner into the control flow. So what happens if we do this? Now this should run. There's nothing. continue on. Still illegal instruction. So I'm not sure what sort of magics is being done to ensure that if a pointer is overwritten, that it's not allowed to be called. Because even though it's overwritten, we overwrote it with the value of that should be in function pointer right now. So I'm not sure if it's because we overwrote this stuff, or there's some other magics happening here. Either way, whatever it is, it makes it such that the code is more resilient to these heap buffer overflows. Now the thing is, we can have both. So I didn't actually need to get at a GDB there. We can have both. We can set the environment for LD preload and run again. Oh, that's not good. Interesting. Oh, right. So let's take away that. So the CFI did not trigger because the pointers were not overwritten anymore because we're using lib hardened malloc. So there must be some sort of pointer checking that CFI does, but the CFI and lib hardened malloc can live together inside of the same binary. It's just that lib hardened malloc will make it such that the CFI doesn't because the function pointer isn't being overwritten anymore. CFI isn't going to say that we've made any illegal instruction calls because we're not calling it anymore. And after I've taken away that code and gone back to how things were, we will see that we can see that we're not exploiting that buffer overflow, even though CFI isn't giving us any troubles here. But that's because we're not actually executing any code that we don't intend to be executed. So thank you very much for watching and listening, and I hope you found this instructional, and I hope that you will consider using lib hardened malloc for your projects. Thank you.